Hello everyone, my name is Lazaros and I will present my work with title Dynamical Investigation of a Modified Cubic Map with a Discrete Memristor. This work has been done with my supervisor, Professor Christos Volos, and also the Professor Ioannis Toubulos at the Laboratory of Nonlinear Systems, Circuits and Complexity at the Department of Physics in Aristotle University of Thessaloniki in Greece. Starting our presentation, before we get into the presentation, we present the outline of our work. In the first part, we will see the introduction and especially the mathematical model of the system. Next, in the second part of our presentation, we will see the numerical results and especially the dynamical behavior of the system in regards to some of the parameters of the system and especially to the parameters K and D. And the final part of our presentation will be the conclusion and the future work. Starting from the introduction and the first part, we present that the ideal discrete memristor can be mathematically modeled by the following system of equations in equation 1, where the V is the output voltage of the memristor, I is the input current of the memristor, and MQ is the memorisance of the memristor. Also, here the Q variable presents the internal state of the memristor. Next, for our system, we choose as a memorisance the following function, which is equals to q squared minus 1. And in order to verify that this memorisance presents the characteristic of a memristor, next we choose a current in the form of I equals to A with a sinus waveform, and we present two figures with the characteristic curve of the memristor. In the left figure, we have the characteristic curve with the current and the voltage of the memristor for Q0 equals to 0.01 and for amplitude of the input current equals to 20 for different values of the frequency. We observe that as the frequency increases, the characteristic curve tends to a straight line. Also, in the right figure, we have again the same diagram, especially the characteristic curve of the memristor, but now for a specific value of the frequency equals to 0.06 and for different values of the amplitude of the current. And with these diagrams, we observe that this memorisance is a memoristic function for our memristor. Next, we choose a map, and especially for us is the modified cubic map, which is presented in equation 3. This map has two parameters, M and D, and now we combine this map with the memorisance in equation 2, and finally we have a two-dimensional map here where the parameter K plays the role of the control parameter, and this parameter is the coupling coefficient between the cubic map and the memorisance. Next, we are going to the second part of our presentation, and we have the numerical results. In the first part of the numerical results, we present the dynamical behavior of the system in regards to the parameter K and for different values of the parameter D. In the first case, we have the parameter D fixed equals to 0.2, and from the bifurcation diagram of the X and Q variable, we observe that as the value of the parameter K is low, the system presents only regular behavior and especially periodic and quasi-periodic behavior, and as the parameter k increases, the system presents chaotic behavior. This it is also confirmed and from the maximal Lyapunov exponent, which is presenting here. Next, we are increasing a little more the parameter d, and now we set the parameter d equals to 1. Also, the other parameters are the same. The initial conditions x0 and q0 and then are equal to the value of 0.1. And now, from this bifurcation diagram of the x and q variable and from the maximal Lyapunov exponent diagram, we observe again the same behavior, but also here we can see that there are periodic regions inside chaotic behavior. Next, we are increasing more this parameter, the parameter d, to the value of 1.5, and here we observe that as the parameter d increases, the chaotic behavior is decreasing. There are more periodic regions and less chaotic behavior. And it is also clear from the maximal Lyapunov exponent diagram, which is presented in this figure. This is the first part of the numerical results, and now we are going to the second part. Here we are making the opposite diagrams. We are presenting the dynamical behavior of the system in regards to the parameter d, and now for specific values of the parameter k. We set the parameter k to 1.6. Again, the initial conditions of the parameter mean are the same. And here we see that the system presents chaotic behavior for lower values of the parameter d, and as the parameter d increases, the system goes from chaotic behavior to period 2 and finally to period 1. This is presented also in the maximal Lyapunov exponent diagram, and also we observe that there are periodic regions inside chaotic behavior. Next, we present a solution for this value of the parameter k, but we are choosing the parameter d equals to 0.2. Here we are presenting the time series of the x and q variable. And next, we are presenting the phase space and the Lyapunov spectrum for the solution, and we have two positive Lyapunov exponents. In the next slide, we are making again the bifurcation diagram, but now the parameter k is increasing a little more to the value of 1.8. Again, the initial conditions and the parameter m is the same. And here we observe that there are again periodic regions inside chaotic behavior, but the periodic regions are more clear in this time. And the maximal Lyapunov exponent diagram confirms this behavior. And also in this time, the parameter d must be increased to very high values in order to go to period 1 behavior, especially to regular behavior, as we saw in the previous diagrams. Again, we present a solution, but now the parameter d is equals to 1.2. We observe that from the time series that the behavior is chaotic of the x and q variable. And to confirm this, we are making the phase space of x and q variable, and we present the Lyapunov exponents of this solution, where we have one positive Lyapunov exponent and one negative Lyapunov exponent. And now we are going to the third part of our presentation, where we present the conclusions. What we saw a modified cubic map with a discrete memristor. Also, we observed chaotic and regular behavior. More specifically, we saw root-to-house through the mechanism of quasi-periodic motion and also the crisis phenomena. And for the two parameters that we studied, the parameter K and D, we saw that for the coupling coefficient K and for different values of the parameter D, we saw that as the parameter D increases, periodic behavior occurs inside chaotic regions. Also, now for the parameter D, we saw that chaotic behavior occurred in lower values for the for specific values of the parameter K, and also we saw that as the parameter D increases, the system behavior becomes regular, periodic, and quasi-periodic, and finally, the system goes to period 1 after one value of the parameter D. Thank you for your attention, and if you have any questions, my contact email is laskari@physics.auth.gr, and again, thank you for your attention.